This is a spring. It delivers a constant force when squeezed and then released. This is a wheel. When the wheel is put in motion using the spring force, it rotates roughly the same amount each time. This is the same wheel and the same spring. Watch how the wheel spins now. The wheel on the right has an arrangement of magnets which can be used to make it spin further. While the push and pull of magnets typically cancel each other out and quickly find a point of rest, these magnets produce a greater force in one direction. This is done with asymmetric magnetic fields, magnetically refractive bismuth, and the natural spins of a magnetic field. Two magnets are illustrated here. The upper magnet has its north pole facing down, and the lower magnet has its north pole facing to the left. The upper magnet is fixed in place, while the lower magnet can slide side to side. Initially, the north poles will repel, causing the magnet to move. However, the south pole will then pull it back. Making the north and south poles asymmetric would help keep the lower magnet moving. Every magnet is already slightly asymmetric. Increasing the asymmetry can create such a difference in the push and pull that a magnet can be pushed away without being pulled back. However, even if it escapes the south pole attraction, it will still be repelled by the next north pole, causing it to slide back and find a point of rest. A magnet's push and pull can be further manipulated using the element bismuth. You may have seen bismuth in a gift shop because it is known for its crystallized appearance. It is known to be diamagnetic, meaning it repels all magnetic fields, but it can also reduce the range of a magnetic field. Magnetic viewing film is one way to see magnetic field strength. Here, magnetic viewing film is placed on top of a magnet with an air gap. Next, the same magnet is viewed with bismuth in place of the air gap. The field strength indicated on the viewing film is tighter with the bismuth. By holding back this part of the magnetic field, repulsion is reduced and the magnet can slide past without stopping. The force causing the motion is the spin of the magnetic fields. There are two spins occurring at the same time, centrifugal and centripetal. These can be thought of as a spin around the circumference and the other spinning inside and out. An experiment with bismuth can confirm the field spin. Since bismuth resists a magnetic field, it will resist the spin, causing the magnet itself to start spinning. When the south pole is facing down, the magnet spins clockwise, and when the north pole is down, the spin is counterclockwise. Let's cover how a magnetic field is made asymmetric in more detail. A method to modify a magnetic field is the Halbach array. This is used in refrigerator magnets. The magnet is strong on one side and weak on the other because of several magnets aligned at different angles. This method adjusts the north and south poles to be mostly on the same side of the magnet. Another method exists to modify a magnetic field, and that is the reflection dish. Again, this can be seen with refrigerator magnets. The steel dish carries magnetic strength from the side of the magnet in contact with the steel to the other side where the steel edges are. These principles are used in the lower magnetic assembly on the wheel. However, the Halbach array is modified to create high asymmetry but still have the poles separated. Reflection dishes are added to the front and back. The front dish helps move the forward magnetic bulge higher and reduces the point where repulsion starts. The rear reflection dish attenuates the south pole field along its length, which further reduces south pole retraction. The upper magnetic fields are also modified. The field is made more pointed, and a reflection dish is added on the back. Stacking two magnets will have an effect at a greater distance. Increasing the distance of the upper magnet's effect helps the lower assemblies to pass by. If the upper and lower assemblies are too close together, the reflection dishes themselves will attract and stick together. The reflection dish on the back limits the part of the field that would repel the lower magnet backwards, as well as further increasing the upper magnet's effective distance. With the spin of the centripetal field, there is resistance for the lower magnet to slide towards the upper magnet. However, once the lower north pole moves under the upper north pole, the magnet will be ejected to the left by both the centripetal field spin and the centrifugal field spin. At this point, the north pole field spins will resist moving together again and will therefore not pull back to the right. If south pole attraction and north pole repulsion are minimized, the lower magnet will slide through. Everything seen here is made of non-magnetic construction materials such as wood, brass, and copper. Steel screws or nails will affect the magnetic fields and eliminate the intended effects of the reflection dishes. Note that the copper is not used for conducting electricity, but as a fastener. First, the center of the wheel is located. The center matters because the upper and lower assemblies have to consistently pass each other with no runout. Next, the rotating bearing is installed. The bearing is made of steel, but it is far enough away from the magnets to not introduce interference. This is what the lower assembly looks like. A copper wire is slid through the holes to hold the magnets in place. The rear reflection dish is just a flat piece of steel. The lower front reflection dish wraps around the top two magnets and has a ramp on the front to modify the magnetic field upwards. The copper fastener is long enough to fit into additional holes drilled into the wood of the wheel. This is what the upper assembly looks like. The upper reflection dish is bent 90 degrees to cover both rear-facing parts of the upper magnets. Another fold is present over half of the bottom. This reduces the magnetic field behind the magnet, which would repel the lower magnet backwards. The upper wood construction is just to hold the upper magnet in the right place at the right angle. A rubber spacer is used to help get the right angle. The upper magnets are tilted downwards at about 43 degrees and installed with a 43-degree twist to a tangent line with the wheel. 43 degrees is based on testing to get the most wheel movement. This number is very close to 42.5 degrees, which is identified as significant in Ken Wheeler's book titled Uncovering the Missing Secrets of Magnetism, 3rd edition. The upper assemblies are set up in groups. Each one pushes the wheel a short distance and into the next upper assembly, which then gives another push. It is possible for the upper assemblies to induce motion from a stop. However, friction still wins for now. There are two limitations to be aware of: static friction and magnet spacing. The wheel assembly is limited by weight because this increases the static friction on the bearing. Bismuth is heavy and responsible for most of the weight of the lower assemblies. The magnetic assemblies have to be far enough apart to prevent the magnetic fields from combining. If they combined, there will be high repulsion and the lower magnet will not slide through. The upper assemblies are spaced far enough apart for the fields to not combine and interfere with each other. However, there is one final assembly that will not fit. Since one upper assembly is missing, the wheel will always slow down here. Asymmetric magnetism can induce motion and make any existing wheel spin more easily and for a longer time.